Here is a PV panel. The panel is connected in series and two parallel string. Single panel rectangle is 250 watts. Totally single string generate 2000 watts. Two string will be generated totally 4000. And then we need to design these parameters. This L is receiver. This is going to be designed based upon the voltage. Single panel voltage 30.7. Total 8 panel connected in series. We have to take 8 into 30.7. And then here the voltage requirement, right, will be 400. So input power will be 4000. Based upon that routine, you have to design. Here you can see that the power of the PV is 4000 input voltage and in switching frequency of the boost converter, and then V out equal to 4000. That means 400 DC bus. And then these are the equations used for calculating LNC. Once you execute this one, you will get the value of LNC. This value going to be used in this boost converter. Next one is we have to design battery. Battery when we connected to the DC bus via this common bidirectional DC-DC converter. So this bidirectional DC-DC converter also going to be designed based upon the PV power rating. Here we have that equation or same kind of equation only, because his bidirectional converter. Here we are using battery. Battery voltage we are taken as 240 volt, and then the bus voltage will be 400. It's like a boost converter only, but the current direction of this converter will be in both directions. Here you have to mention the power of the PV, because we have to design that converter also rating method of PV power. Here you have to take the power of the PV, and then input voltage will be 20 into 12, and then output voltage 400, switching frequency will be 10 kilohertz. And then once you click this one, you will see the value of LNC here. This is the value of LNC. Same value you are going to use here. Next process, you have to design LCL filter. LCL filter also going to be designed based upon the power rating of a PV is 4000, and then battery you are told me it will be delivered 1 kilowatt. So you have to design for 5000. Here I will take 5000 watts. DC voltage is 400. Switching frequency is 7500. AC voltage is 230. Frequency 50 Hz. So this is an equation for calculating L1, L2, C for LCL filter. Once you execute, you will get the value of L1, L2, and C. This value is going to be used here. L1, this is L2, and this is C. Next process is control of PV. For that you have to measure the PV voltage and current. The PV voltage and current will be input for this MPPT algorithm. Based upon input voltage and current, it will be generate the duty cycle. This duty cycle when we process via PWM generator. This will be generate the pulse. So this pulse will be used for control this IGBT of this boost converter to extract the maximum power from the PV panel, and also boost the voltage from around 245 volt to 400 volt. So next process, here you need to control this bidirectional converter will be controlled by means of voltage control method. For that you have to measure the load voltage. So load voltage going to be compared with 400 volt, and then the error voltage will be processed via PA controller. This PA controller will be providing a duty cycle. The duty cycle we are taking averaging value, and then it going to be processed to a PWM generator, and then it going to be generate the pulse. So this pulse is used for control this 2 IGBT of that bidirectional converter. It will be control this converter by maintaining the voltage in the DC bus up to 400 volt. Next one is you need to control this inverter. For controlling this inverter, here we are using fuzzy logic based energy management system. The two input, one is PV power and one is SOC of the battery. Here you have to feed PV power and SOC of the battery. Based upon you have to generate the current reference. Here you can see that fuzzy coding here, right? Fuzzy already we created here. I'm going to load that one. Put from file. Here we have the fuzzy file. We did have two inputs, PV and SOC. PV power will be scaled down in between 0 to 1. That means actual power is 4000. It will be scaled down to 0 to 1 scale by dividing with the 4000. And SOC actually in between 0 to 100 actual data, that will be scaled down to 0 to 1. And we have separate that the PV into 4 scale: 0, small, medium, and big. And SOC will be scaled down into 5 membership function: 0, small, medium, big, very big. And then output high reference for that inverter, it have 5 negative big. That means the high reference will be in between minus 1.3 to 1.3. It will be in between. That means it have NP, NM, Z, PM, PP. So next you have to use the relating equation. Here we written the 20 equation. If PV power is 0, SOC of the battery is 0, then I reference is negative. I reference is negative means negative bit means we are taking power from the grid. Same way for we written the several codes. For example, PV is 0, the source is medium, then we are taking the negative medium current from the grid. Based upon this, for example, if PV is big and the source is very big, the I reference is positive bit. That means we are sending power from the battery grid to AC side. You have to take the logic. That means you can see here the ruled surface. So now the PV is very high and the SOC of the battery is very high. The I reference will be positive higher. So what is the meaning? So we are sending power to the grid. When PV is low and the SOC is low, I reference is minus negative, minus 0.96. So negative maximum. That means we are getting the power from the grid. When both will be nearer to the 50%, the value of I reference will be 0 to 0. Based upon that, the reference current will be controlled in the inverter. Here we are measuring the PV power divided with the 4000. Here we are measuring SOC and divided with the 100. Here we will get a per unit PV power and the SOC in per unit. The output of the first will be I reference in the range of 1.3 to minus 1.3, and then here I am going to multiply it with 10. Here if multiplied with 10 means normally we are sending power around 3000, and then this I reference in the DC form. We need to convert it to AC form by multiplying with the sinusoidal. The sinusoidal waveform is generated by means of measuring grid voltage is going to be processed by PLL. It will be generated the omega t multiplied with the sine, we will get the sine wave. After its multiplication sine wave, you have to convert ABC to DQ form. Here we are converting ABC to DQ form. Here we will get the D reference, Q reference. So next you have to measure the grid current. Here we have to measure grid current, and grid current will be converted into DQ form by using AB to DQ conversion, and then this D reference, Q reference going to be compared with this DQ, and then it's going to be processed via current controller. After processing via current controller, it would be generally the control signal in the form of DLQ. Then it's going to be converted into AB form, and then you have to take only A quantity, and it's going to be processed via PWM generator. This PWM generator will be generate this pulse. This pulse will be going to be control this inverter. It automatically control the current of this inverter in both direction. So it will be take the current from this direction to this direction. That means take the power from the DC bus to AC bus or AC grid, and then it transfer the power from AC grid to DC bus according with the condition of the PV power and the SOC of the battery. Here I create the change in irradiation condition. Initially the irradiation will be 1000. After this 500 is going to 10. Again it comes to 500, 1000. Initially it will be high and then comes to 50% and then comes to very low. During this time battery will be going for a charging mode, and it will be supply the power to this AC load, and also grid will be supply some power to the AC load also. So this is a point of common coupling. This is the point of common coupling. So here you are measuring the current. This is the current injected to the grid from this inverter. Here you have a different scope. This is first scope. Here we are measuring the PV voltage, PV current, PV power. You will see that the voltage, current, and PV power by that for changing irradiation condition. And this is a DC bus voltage, and then this is a battery voltage and current. And here we are measuring the PV power, load power, associate the battery and the grid power. And then here we are measuring the grid voltage and grid current and the point of common coupling. And here we are measuring the frequency of the system. Already we simulate the model. Here you can see that initially that irradiation will be 1000. So it will be that means because of DC voltage setting, it will be having some oscillation. After sometimes is, if you suppose you are going to leave for a long time, it will be goes to 4000 watts. For 500 it will be generated around 2000 watts. For 10 watts per meter square it will be generated 0. For 500 it will be generated 2000. For 1000 watts per meter square generating 4000 watts. And also here you can see the battery detail. The battery current will be changing according to the change in irradiation condition. That means it goes for charging and discharging mode. Here you can see the SOC of the battery. Here you can see that from 0 to 0.6 it is in charging mode. From 0.6 to from 0.9 it is in discharging mode. from 0.9 to 1.5 it again goes to charging mode, because during this time 0.6 to 0.9 PV power will be 0, that's why battery will be charging mode. And also here you will see that the grid voltage and the grid current are in sinusoidal. So it will be sinusoidal, both are in phase each other. Next process, we are getting the sinusoidal current in the system. And also here you can check the frequency. The frequency always maintain at 50. When we change the condition, for example, here I'm going to make SOC is 10%, and then simulating the same model. Here you can see that sometime battery goes for recharging mode because it having enough power. Here I'm going to simulate when making SOC is 10%. Now the current will be negative. Now you can see that we are getting power from the grid. We are getting power from the grid. Here you will see the phase shifting. Here you can see that there is a phase shifting from the voltage and current because we are getting power from the grid. That's why the phase shifting is between voltage and current. And also the frequency is maintained constant at 50. And here you will see that the SOC is keep on increasing. Here you can see that for changing irradiation condition and the SOC is less around 10% only. It is always in charging mode, even though power of PV goes to 0. So it is getting power from the grid. So here you can see that the grid current and voltage will be in an opposite phase because we are getting power from the grid. So this is working of this model. Kindly use this video for understanding. Thank you.